Okay, so in this lesson we're going to start talking about a concept called Gauss's law and kind of give some ideas or give some basic background information about Gauss's law when we get into looking at another way to calculate electric fields. Now the reason to use Gauss's law is actually pretty simple, and the reason is if you're trying to solve for the electric field of a distribution of charged particles using integration, almost always your solutions are very difficult. It's usually a very challenging process to do. The reason for that is almost always the integral that you're trying to set up is hard to set up in the first place, and even once you have it set up, it's usually something that's difficult to integrate. In fact, some of the ones in my previous lesson video, I actually used a table of integrals to figure out what the solution was rather than integrating it out by hand because they are that challenging to do. So this is actually an easier way to find electric field for some situations of distributions of charge. Gauss's law usually depends upon you having some sort of either uniform or symmetric distribution of charge that you can use in order to develop an equation to actually plug in to solve out for the electric field. And we actually make use of something called electric flux in Gauss's law. And so it's actually electric flux that allows us to connect to electric field when we do Gauss's law. So we think about what electric flux is. So let's assume we have this sheet here, and so the sheet has an area A. So think about it like a sheet of paper. And let's say there's electric field passing through the sheet of paper, and it's passing at some angle theta away from the normal or perpendicular. What electric flux really is it's a measure of how much electric field, if we really want to think about it, passes through the sheet of paper. The way to think of electric flux, I think of it in terms of like water moving down a pipe. What electric field is really telling you is the rate at which water is moving down the pipe. You need to know the area of the pipe, and so if you know the area of the pipe and the rate at which water is moving through the pipe, you can figure out how much water moved through the pipe. Similar here, the electric field really talks about almost like a rate of which this happens through this area. And electric flux is really talking about a total quantity of, well, electric field that goes through a particular area. So the way to calculate electric flux is to calculate the electric field times the area. And I say times a dot product with the area vector. So the area vector happens to point perpendicular to the area, and so this is a dot product. Electric flux happens to be a scalar. It really just tells you a quantity. It may be a negative number, meaning that your electric field goes one way and the way you've defined your area is opposite of that. But if we actually calculate the total electric flux of a surface, we would actually add up all these individual little pieces. And if we do an infinite summation of these, we actually end up with an integral. To be more specific, this is what we would call a surface integral. Where you're taking E dot dA, where the surface integral of dA ends up being the surface area of a surface. So let's look at some closed surface. So here I've picked let's just say a spherical closed surface, and I've put a charge Q outside of that surface. If we look at electric field lines coming from Q, the thing with electric field is it always points away from Q. There are some places where the electric field is entering the surface, and some places where it's exiting the surface. In the points here on the left-hand side, those are places where flux is negative. Electric field is pointing into the surface. These are points over on the right-hand side where flux is positive. Electric field is pointing out of the surface. What happens if you add up all of these is the number of electric field lines that entered the surface on the left is equal to the number of electric field lines which pointed out of the surface on the right. And so the net flux through this surface is 0. So really what flux is a measure of how many of these electric field lines go through a particular surface. But what if I put Q inside the surface? What is going to happen in that case? So if I have a closed surface and all my charges exist outside that surface, the net flux through that surface is 0. But what if I put Q inside the surface? What's worth pointing out is that all of the field lines point outward. So the net flux is not 0. And all of them point out of the surface. But is there a way I could calculate the net flux? The answer is actually yes, and it's unexpectedly really easy. all I need to know is two things. What is the charge enclosed Q, and then this value epsilon naught, which is called the permittivity of free space. This is a value that's on your equation sheet that you have for the AP exam. And it is a value that is equal to, let me find it here, 8.85 times 10 to the negative 12 Coulomb squared over Newton meter squared. Happens to work out that the K in Coulomb's law is related to epsilon naught, that K is equal to 1 over 4 pi epsilon naught. So I can calculate the total flux, or the net flux, in a closed surface just by knowing the number of charges, or the total charge that's enclosed by that surface, and dividing by epsilon naught. Now the neat thing about this is it doesn't matter what the shape of my surface is. It could be any random weird shaped surface. Here I have this kind of weird, whatever you want to call this shape, and I've put some charges inside and some charges outside, and I want to know what is the net flux through this surface. So it's worth pointing out that net flux is equal to charge enclosed divided by epsilon naught. So the only charges that I'm interested in are these three charges that are enclosed. The plus 3q and negative 6q outside don't matter. So the net charge enclosed is plus q plus 5q minus 2q. And so the net charge enclosed is 4q and then divided by epsilon naught. There we go, I would have found the flux through the surface. So actually finding net flux through the surface is pretty easy. All you need to know is how much charge is enclosed. If you can find net flux through the surface, you can actually work backwards to figure out the amount of charge that's actually enclosed. Now, how does this actually work when we do electric fields? Remember that we said flux was equal to charge enclosed over epsilon naught, but net flux is also equal to E dot dA, that surface integral. So what if we put these two pieces together? We end up with is a way to calculate electric field by creating a closed surface and using the flux through that closed surface. The flux through that closed surface is only related to the amount of charge that's enclosed by the surface. It has nothing to do with all the charges that are outside the surface. Now, as we'll see in the next lesson, when we look at some applications, if we choose our surface wisely and choose to define the system in a smart way, I can actually make this formula pretty easy to solve out. Now it's worth pointing out in this formula, it looks like the right-hand side is an integral and the left-hand side is just plug some numbers in. The reality is you can choose your surface so that the right-hand side, that integral almost never needs to be integrated. Unfortunately, on the left-hand side, where it says Q enclosed, there are some situations where you need to define Q enclosed in terms of an integral. And we'll look at that in kind of the next lesson, looking at some applications of how we apply this law to calculate electric field.